Second half of this chapter. First half of the chapter, we just talked about solvents, solutions, suspensions, colloids, just different terms, different kinds of mixtures. But for the past week, we've been working with formulas, equations, and calculations. Okay, the last one we got to do here today, and we're going to be using this. I hope actually it was a lot better for your class. Your class, I did this for about 20 minutes, and then they went right back to the lab, so it was fresh in their mind. Tomorrow, you have a double period, and that's when you'll be doing the lab, so it won't be fresh in your mind. All right, so the only good part is you'll get time to work on the problems here today. In class, they didn't really have any time. But I'm just saying, all of this, every single thing up here, this is an extremely comprehensive lab, including stuff we haven't seen in a while, like stoichiometry. Is going to pop up its head up in the next lab, which is why we're going to need actually a full 2 periods to do that lab. All right, we're going to be mixing things together and calculating percent solutions. We're going to be diluting them. We're going to be calculating molarities. We're going to be mixing them together to make a precipitation reaction, and then we're going to be calculating how much of that we should get.
I'm not.
That's nice. No surprise. Anyway, whoever's here is doing the lab. I'm sure other people won't be here either. Anyway, dilution calculations. That's the last thing I'm going to teach you about the calculations. We're going to learn how to determine the new concentration if I dilute something, or how to prepare a concentration if I need it. And this is an extremely useful skill for college laboratory situations. Because unlike my class, where everything is laid out for you at your table with the exact concentrations that you need, because we only have either 45 minutes or maybe an hour and a half to do a lab. That's not what happens in college. You do not get everything laid out for you with the proper concentrations. And here, just mix these two together and see if you get a precipitate. Or mix these two together and see what happens. No, you're going to have to make your own solutions. Okay? So here's what I'm saying. You'll go back to a stock room. If you need it, like, don't copy this. Just wait for a second. Actually, I want to do the equation first. Before I get to the equation. You'll go back to a stock room. And they'll have a big stock bottle that'll be a certain concentration. You'll have to dilute that. Okay? It's not what you need. For this lab, you need a 1 molar solution. But you go back there and it's 12 molar. What do you do? All right, for this lab, you need a 2 molar solution. And you have to go back there and you get the solid and you have to mix it together to make that 2 molar solution. You need a 5% solution. You go back and get your salt. You get your water. You mix them together. You make a 5% solution. You have to do that. In my class, you pick up the 5% solution. You pick up the 2 molar solution and you just pour it into the test tube. Okay, so that's why you need to know how to do these things I'm about to show you. Now, some of them are really easy. Let's just use a little common sense on some easy ones. Say, don't copy this down. Say I had, definitely don't copy that down. Say I had a 2, don't write this down, molar solution of something. And I had 100 milliliters of it. Then I went and I poured 100 milliliters of water into it. 100 milliliters of water into that. What do you think the solution concentration is now? 1. See, people kind of know that. I cut it in half, didn't I? Right? I had 100 milliliters of a 2 molar solution. I added 100 milliliters of water to it. I've cut it in half, right? Everybody agree? You all good with that? Now, I'm going to show you a formula, you just came up here a second ago, that we'll be able to do. Obviously, it won't always be that easy. 100 milliliters of 2. So we can do it for harder problems as well. Okay, and that formula looks like this. M1V1 equals M2V2. It is a very useful formula. Because you will have to, I'm telling you, when you go, if you take any chemistry in college, they're not going to just have the solutions made up for you. Now, obviously, M1 and V1, M2 and V2, they should be pretty obvious things. M's probably stand for molarity. V's probably stand for volume. There are some tricks to it, though. M1 and M2 are the molarities of the solutions before and after. V1 and V2 are the what? Volumes before and after. Now, there is a little trick to that. We'll see in several of these examples what you might do as a mistake. All right? But for the most part, these are done the way I've taught you how to do problems that have an equation like this. We've seen equations like this multiple times throughout the year. And you shouldn't worry too much. The equations at the end of the year I will have a formula card, basically. Like you have, anybody have a formula card in physics? You're allowed to use a formula card in physics, right? Well, it's going to be like that, only I'm going to have it up on the board here. It's going to have every formula we use throughout the year, okay? And you say, well, I thought the final is not going to be comprehensive. It's not, technically. I'm not going to have questions specifically on, stuff that I already covered in the midterm. However, as you know, many of these things have popped up in the second half of the year. Have we used stoichiometry in the second half of the year as well? Yeah. And we're going to use it again today in lab. So that is not, even though I taught it in the first half of the year, it didn't go away. So you are going to have to use a lot of these equations, and I will give them to you on the final. There have been quite a few. How have we used these equations up till now? Same way. I always said, write down the given information to the side, and pick out the stuff from the problem. And this stuff is not so easy to pick out. Take a look up there. Oh, I didn't give the question. There we go. Try the question first. All right, same thing. M1, V1. Okay. This is not so easy to pick out sometimes. Need you all to look at that and see if you can figure out what's what. What's M1, what's M2, what's V1, what's V2. Okay, look up there. What do you think your M1 is in this problem? Your initial molarity. Read the whole question. Raise your hand. What do you think, Zach?
18 molar.
18.0 molar. H2SO4. Okay. But what about V1? What's your initial volume? It is my unknown. Because, let's go back and show you what I mean by that, what we're reading here. Ready to, this is the kind of problem I have to do. You've never really had to deal with, but I have to do all the time. I don't just give you 18 molar sulfuric acid. It's nasty stuff. I wouldn't want you playing with this. We have used sulfuric acid, and we will use it in the future. But generally, I give you maybe 1 or 2 molar sulfuric acid. Same thing with hydrochloric acid. I don't give you 12 molar hydrochloric acid. It's way too strong. It would be fuming. It would choke you. All right, so I have to dilute it. So I know for this lab, I need 1.40 liters for the lab. And I know I want a 0.90 molar solution that you guys could use. I have to figure out how much of this I have to add to make up a 1.40 molar solution. And so that's my unknown. Now, M2, what I want it to be is what? What do I want the new solution to be? 0.900 molar, correct. And the V2, my new volume, how much of it do I need? 1.40 liters. Got it? All right, good. So let's do the problem. M1, V1, M2, V2. What am I going to do to both sides? I got a wrong answer on this, believe it or not, at this point in the year. What will I do to both sides? Divide by what? M1, because I'm looking for V1. People just tend to, they figure the first thing written is what they're always looking for, you know? It's not always. So V1 equals M2 V2 over M1. My M2 is 0.900 molar. What's my V2? 1.40 liters. And my M1 is 18.0 molar. Get your calculator out. What does V1 equal? Jared, what'd you get?
0.07.
0.07. Significant figures wise, it should be
0.070.
0.7. Well, how many significant figures do we have here? How many we have here? Three.
0.0700.
Right. Okay. Liters. Now, that's all well and good, but tomorrow you're doing a lab, and you're going to be doing this in lab. You figured out, you did the problem, but do you know what it means? Here's what it means. You would have to take 0.0700 liters, or how many milliliters is that, by the way? Yeah, if I'm making this, don't write this down, but if I'm making this up, you don't have to write this down. If I'm making this up in the back, in the stock room, I'm trying to do this. I'm going to take 70 milliliters of that acid and add it to what? 1.40 liters of water? No. 1.40 liters is what the total has to be. What am I going to add that 70 milliliters or 0.070 liters of acid to? What's that?
Water.
How much? Water. I have to subtract away the 70 milliliters from that, right? So how much water would I actually add to it? Or add this to?
1.33.
Yeah, I would add it to 1.30, right? 1.30? Is that right? Or is it 1.33? 70. That's what 1.30. Right, because 70 milliliters, 0.07. No, wait.
0.33.
0.33, right, 0.33, sorry. Right, that is true. So basically, 1,330 milliliters of water and 70 milliliters of sulfuric acid. Right? Okay. That's, by the way, one last thing about this. You would always add the 70 milliliters to the water. I would never add the water to the acid. Okay? You don't have to, again, you never really have to worry about these things because they're just already made up for you in our lab. They won't be tomorrow. But you don't usually have to worry about these because I mix them up for you. But if you were to add water into 70 milliliters of concentrated sulfuric acid, it's going to spatter and get really hot and break the beaker and jump up at you because it gives off a lot of heat. Okay? All right. All right. Good enough. Now, so that's the kind of problem that I have to do quite often. Now, let's do a problem that you're going to have to do exactly like this one tomorrow in lab. Copy this one down. And by the way, that last problem is the kind of problem you would have to do in a regular lab. All right, look at this guy. This is a perfect example. The reason I'm doing this one is I'm just prove to you why a formula looks like it does. Because I'll bet you, if some of you think about this one for just a few minutes, you can give me the answer without even a calculator. Look at what I do to this problem. What will my new concentration be? What do you think? 2, right. You see why it's 2? I had a 4 molar solution, I had 50 milliliters of it. And I added 50 milliliters of water to it. So I doubled the volume, I'm going to cut the concentration in half, right? Makes sense. Now, let me show you, after I get done with this problem, why we get to and what makes sense about this equation. Why is it M1V1 equals M2V2? You'll see in a second, watch. All right. Same thing though, M1 equals, V1 equals, M2 equals, V2 equals. You need to be able to pick them out correctly. I will show you the mistakes you're going to make because you're not thinking, because you're basically just doing them by plug and chug and not understanding them. What's my initial molarity, first of all? Read carefully. My initial molarity, what is it? What's that? I heard, did everybody say 4.0? That's correct. Now, last class, somebody was saying, That's what you're looking for. Am I looking for that? I'm not looking for that. Some people, the reason they said that, I realized later on, it's the last thing written. Last thing written can't be M1. Yes, it can. Let's look at what the question says. Let's read the question. It says, find the new concentration. That's my unknown, M2, new concentration. If this many milliliters of water is added to this much 4 molar. So it was 4 molar. What's it going to be when I add the 50? That's how you have to read. So this guy is 4.0 molar. Good. What about V1? What's my initial volume of that 4.0 molar? 50, right? And here's the next mistake people will make. V2, 50. Is that right? Yeah, it's 100. You have to realize that you added 50 to 50. You now have 100. Good. All right. So now the rest of this problem is pretty easy, obviously, but I want to show you the reason I told you I'm doing this one. It's a nice, easy one. Well, 2 reasons. One, this is exactly like what you have to do tomorrow. I'm going to tell you to dilute something by adding some water to it, and you're going to have to tell me a new concentration. And 2, I want to show you what why it works out the way it does. M1 V1 equals M2 V2. I'm looking for M2 this time, so I'll divide both sides by V2, right? So M2 equals M1 V1 over V2, which is 4 times 50 over 100. Obviously, 4 times 50 over 100 is 2. Milliliters cancel. And let's see if you can figure why I showed you this. Everybody got that? Look, here's why I showed this to you. To get your new molarity, you simply take your old molarity and you multiply it by how the volumes changed. In this case, they went from 50. They doubled 1/2. You're basically multiplying by 1/2. As you know, common sense-wise, it makes sense to do that. Mathematically, that's why that formula looks like that. That's why it's M1 V1 equals M2 V2. It couldn't just be any other way. It couldn't be M1 over V1 equals M2 over V2. That would not give you the same answer, okay? Because it wouldn't do what it was supposed to do. So again, calculations, formulas look like they do for a reason. D equals M over V. Remember the delta H was MC delta T one. I showed you why. It's M, mass. How much of it? That's how hard it is to heat it up. Temperature change, specific heat. What exactly are you heating up? It's not like biology. It's not like other classes where you just memorize your way through it. You actually, these formulas mean something. Same thing's true in physics, by the way. A lot of times you get lost in the middle of the formula. You memorize your way through the formulas, and then you just plug and chug out your answers. But it should make sense. For example, if you find yourself diluting something in a problem and getting a higher concentration for an answer, you did something wrong. That's the kind of stuff that you'd pick up on if you knew it was making sense. All right. This one I added for a good reason. He has a little trick to him at the end. Pretty much, I want you to do this one on your own right now. Set it up, M1, V1, M2, V2, and do it on your own to get your answer. But then I want someone to explain that answer to me because I bet you would do it wrong if you were in the lab trying to do it. All right, let's see how we're doing. Keep going. I'm just going to write my answers down. I would hope you all have the same thing. Y'all have that so far? Right? Is that what you have for your stuff? M1, V1 equals M2, V2. Solving for V2, divide by M2. V2 equals M1, V1 over M2, which equals 1.40 molar times 3.0 liters over 0.800 molar. What do I get?
500.
500?
5.3.
Oh, 5.3? Anybody else get that? 5.3? 5.3 what?
Later.
Molar cancels, liters. All right. Now, that is not your answer. That is not your answer. That is how much the new volume will be. But the question didn't ask me that. The question said, how much water do you have to add to 3 liters? That's the total of 3 liters and the other stuff you added. So what's the correct answer? 5.3 liters minus 3.0 liters, or what? 2.3 liters is the correct answer. Got it? So you see why this is confusing. This really is a thinking man's problem. It's not like you could just plug and chug every time. At the end of this one, I had to realize that's not the right answer. At the end of the previous one back here, I said, well, yeah, that's the right answer, but it means I'm going to add that to how much water. It's not going to be to 1.4 liters of water. I got to subtract that 70 milliliters away. So you have to keep all that in mind when doing these.